Groups are usually treated as one of the central objects in abstract algebra. Because of the word abstract, many people will struggle to see how a particular result works. But equipped with some intuitions, you might see why some theorems are blatantly true and instead say, what else could it be? Groups are mathematically defined to be something that fulfills these axioms. Although it is amazing how an entire theory is founded on these axioms, we will ignore these for now. In this video series, we will treat a group as symmetries of an object. The object can be a plane figure, usually a regular polygon like a square, a solid like this regular tetrahedron, or even a real number line. And the symmetries here mean a transformation that preserves both distances and the object under study. So this figure with two triangles doesn't have a symmetry that looks like this, because the distance between the red dots changes after the transformation. So in this case, the transformation does preserve the object, but not distances, and so it is not a symmetry of the object we are studying. When defined this way, we can see that symmetries have these kinds of properties, namely, any composition of two symmetries is a symmetry, because all symmetries preserve distances and the same object. And compositions are associative. This means that given A, B, C being symmetries, both expressions tell you to do the same symmetries in the same order. Also, not doing anything is a symmetry, because not doing anything definitely preserves distances and the object. We call this symmetry of not doing anything the identity. And the last property is that we can always undo a symmetry, and this undoing is a symmetry itself. And these four properties are what's captured in the group axioms. All these properties are pretty intuitive, and you should keep these in the back of your mind because we will subconsciously use them a lot of the times. Symmetries are not only useful for visualizing groups themselves, but also something called group actions. Again, there are some axioms regarding what a group action is, and again, we use symmetries to visualize this concept. The key here is to see what symmetries do to the object. We usually see this by only analyzing what symmetries do to the vertices. For example, in this tetrahedron, we label the vertices as 1, 2, 3, and 4. So here, we take the set X to be 1, 2, 3, and 4. And notice how these vertices change under the symmetry. So now, vertex 2 becomes vertex 3, which becomes vertex 4, which becomes vertex 2 under this rotational symmetry. So if we now denote this rotation as sigma, then we say that sigma star 1 equals 1. Here, the star simply means acting on. It is not a multiplication in the traditional sense. Similarly, sigma acts on vertex 2 to give vertex 3, and so on. But of course, the set of vertices is not the only thing that sigma can act on. We can also consider the set of edges. Here is an example of sigma acting on the edge connecting vertices 1 and 2. And here, the cross sign has nothing to do with multiplication in the traditional sense, it just means acting on. The only thing we need to keep in mind is that when we act sigma on something in the set, it outputs something in the set. And this has to be the case no matter what set you take, which can be vertices, edges, or faces. And sigma is just one element in the group of symmetries of the tetrahedron, and we can define actions like what we did to sigma. So to be clear, the symmetries of an object form a group. And this group acts on the set of vertices, edges, or faces to give the same set back. And the set here can be anything you want, as long as the set being acted on is the same as the output set. Now I want to emphasize that this video series is for the development of intuitions only, but I hope it does enhance your understanding in group theory if you wish to really dive into it. If you enjoyed this video, give it a thumbs up and share it. Don't forget to subscribe with notifications on to stay tuned to this video series. See you next time!